All right. Okay. So welcome to the homework for bootcamp. So just to give a quick breakdown of what we'll be doing today. Well, first we'll introduce the assignment. The assignment is kind of different from from the way you've been working so far for your P1s and P2s. So we are introducing a new assignment format. And we'll go through the format and some of the reasons why we decided to do it this way for this assignment. And then we will introduce homework for P1 and homework for P2. So we'll introduce some of the tasks you have to complete. Sorry, are you here for, oh yeah, can you take a seat? Hackathon, yep. We're doing the boot camp first for homework 4. Yeah, well, they're all remote. Yeah. You get sometimes. So I was just saying, we are introducing homework 4. So like there's a new format of the assignment. So the handout is different. The assignment that you've done it so far is different. So we'll introduce the assignment, we'll introduce the workflow and some of the tasks you have to complete. Thank you, by the way. I was the only one, so it's nice to see somebody else. Cool, cool. All right, so so essentially for both homework for P1 and homework for P2, you'll be introducing this library that we are calling homework for lib, right? So the reason we are doing this is kind of threefold. So first, we would like to enable you guys to do most of your implementation work locally, right? So towards that end, we have like this whole process of setting up your environment and getting things set up locally. And so you should be able to do most of the implementation work on your local computer before finally moving to a GPU compute to do the training, right? Another thing what we wanted to do is we kind of wanted to do the P1 style of testing for P2s too. So that's another reason for this assignment design. So towards that end, we'll be providing you with a full test suite that you can use to test your implementations. And I'll be demonstrating some ways you can do that. It'll also be documented in the write-up and in the notebook, right? And then the last thing is this is your last assignment. This assignment will be like the culmination of everything. You kind of be the culmination of everything you've done so far. So we want you to build a full deep learning pipeline. So the assignment will be sparser. You'll have to implement much more of the pipeline than you will have been used to doing for your other P2s. So towards that, you'll incrementally build this library. And yeah, another thing we would recommend you to do is to just get started early because there'll be the overhead of getting used to this new format of delivery, and there'll also be like a lot more implementations to do compared to your previous assignments. Right. So we've posted the handout on the Autolab. Just to remind you, homework for P1 and homework for P2 have the same handout, right? You'll also be doing a little bit of training for homework for P1. And you'll be implementing this library, as I said before, called homework for lib. And the components you'll build will be reusable across both assignments. And we'll also provide you with a test suite. All right, we have setup instructions for so we're supporting your local environment, setting up on Colab, Kaggle, and PSC. Make sure you follow your setup accordingly. Follow your setup instructions accordingly, and reach out to Piazza if you get stuck. So right now we'll be doing the local way, right? Just to demonstrate how you could go about doing this. So you'll upload your handout. Your notebook should be on the same directory as your handout. And once you have that done, you get all your imports should pass. Or we'll also ask you to install this environment with all the dependencies. Once you've done that, you can just select the environment that we ask you to install, and then all your imports should pass. All right, so let's turn to the things we have to do in homework 4P1, right? So in homework 4P1, you will, like I said, you'll be incrementally building components of homework for lib to build, train, and evaluate decoder-only transformer model from scratch. So by decoder only, you can think like GPT-2 style, right? So you will first build all the components, then you will use it to train in an autoregressive language modeling task. More on that later. And then finally, you'll use it to generate text. All right, so let's dive deep into what our training objective is. So for our training objective, we want to train this model to be able to model the probability of a sequence of tokens, right? So here we have, so let's say we have a sequence of tokens x1 through xn. We want to be able to model the probability of that. So we'll decompose it using the product law into a product of conditional probabilities, P of xt conditioned on P of x1 to xt minus 1. So, and then our transformer will essentially model these conditional probabilities, right? So we want to be able to assign probabilities to the next token given a sequence of previous tokens, right? So the way we'll train this is our goal is to train this in a self-supervised manner. There won't be any explicit labels here, but we want to be able to just use vast amounts of unlabeled text to do this kind of modeling, right? So we're given a token sequence of x1 to xn minus 1, we can assign a probability or model a probability distribution over the nth token, right? So here we have an example. So let's say our sentence is, I swam across a river. So given I swam across we would want our model to assign, or we would want our model to model a probability distribution that assigns a high probability to river, right? If I have I swam across the river, we would want the model to assign a high probability to the fact that we should end the sequence generation right now. So predict the EOS token, which we will see in a bit. But now, so taking a piece of text, splitting them this way and processing them independently will be very time consuming, right? So if you imagine a large corpus of text, doing this kind of processing will just blow up there'll just be a lot of computation for this, right? So the way transformers are built is that they aim to handle all these, they aim to process all these sequences in parallel, where each token serves as both the input and the target, right? So to enable this, we'll need some mechanisms to facilitate this. Right, so the way we do this is we have our input sequence of tokens. Let's say I swam across the river. For our input, we append a special token called the start of sequence token. And for the target, as you can see here, we append a special token called the EOS token, or the end of sequence token. And this becomes our input and target. So what we're going for is that we want every token in the target to correspond to, so let's say a token at position I in the target should correspond to every token from 0 to I in the input. So the way we've mapped it here, across would correspond, so across is at 0, 2. So everything up to 0 to 2 should correspond to across, right? So our model should condition on SOS, I, and SWAM to assign a probability to across, right? So this is kind of sort of like the conceptual right shifting, right? We right shift the inputs by one token and left shift the targets by one token, and then append by appending these like SOS and EOS tokens to ensure that we have that correspondence, right? Now, but when we train the model, let's say I want to predict across given SOSI and SWAM. The model should not be allowed to cheat, right? So we apply this thing called a causal mask, where for each token in the target, the model is only able to see the previous token. The model is only able to see the tokens that come before it to make its prediction, right? But then also we need to be able to process all of this in GPUs. So we'll need like nice, our tokens will all be variable lengths. So we want to construct this nice square-sized batch. So we'll also use pad tokens the way you've been doing in homework 3. And we'll also need masks for that too, so that we don't attend to these padding positions too while making these predictions, because they're just there for convenience and don't really contribute to meaning. Shouldn't contribute to while making predictions. Right. So in a nutshell, so our entire training processes does this, right? So you have this sequence of tokens. We'll go through tokenization and stuff. So we have raw text that we will first tokenize to create these sequence of tokens. And then we'll use an embedding layer to create this sequence of d-dimensional vectors, right? You'll use nn.embedding for this. So once we have this sequence of vectors, we will inject positional encodings, which will be the transformers notion of transformers don't have recurrence or anything else to rely upon for positional information. So they'll use these positional encodings for their notion of order, right? And then you'll pass them through this transformer, which will do like a bunch of transformations that you'll implement for this homework. Finally, to get this output sequence of, again, you'll get this output. After this transformation, you'll get this sequence of vectors, which will be your model output. They'll be d-dimensional. But now we want to model a probability distribution. So we'll have to project this sequence into the vocabulary space, right? So you had your sequence of N cross D shaped output from the transformer. You will project it to the vocabulary space to get N cross K, where K is our vocabulary space. Now, each column will then model this probability distribution at that time step, right? So we have we can apply a softmax to that columns. So we have our N cross K output logics after the projection, and we can apply softmax to each column to model probability distribution for that token conditioned on the previous tokens, right? And then we can train this using cross entropy loss, and essentially our goal is to maximize the likelihood of the training data, right? And once we've done this, you'll be able to generate, you want to model token dependencies in an autoregressive manner. And once you've done this, you've essentially trained a model to generate token sequences conditioned on the previous tokens, right? So we'll be using perplexity as our evaluation metric for homework 4P1. It's essentially how surprising model finds a particular piece of text. So if you have the text, it is raining, the different models might predict it's raining outside, which seems correct, which is raining banana tree, which is strange, but at least they're valid words, or you can have this complete gibberish, right? So we want our model to maximize the likelihood of predicting sensible text given this prompt, it is raining, right? So we'll use this metric called cross entropy. And essentially, you can think of it as like how confidently your model is, how confident your model is at its prediction, right? So the effective number of choices it considers at each step of the decoding process, right? So a perfect model will always assign a probability of 1 to the correct token. A bad model will like assign a probability of 0 to the current token, which so it'll have infinite perplexity. And a baseline model, so like if a model that assigns uniform probability to the entire token vocabulary space, it'll have a perplexity equal to the size of the vocabulary, right? So, but you will be reporting per character perplexity. And then so after you've trained this model, you'd like to generate text. Given a prompt, you'd like to generate text, right? So for this assignment, we'll only require you to implement greedy search. But you can also, there's other ways of generation too, like top case sampling, beam search, and all that. You can go through it in the write-up. Yeah. So let's take so what do we have to do for P1, right? So for homework for P1, there's 2 broad tasks. First, you will add this whole core backbone of transformers, which is the multi-head attention mechanism, to your MyTorch library that you've been building throughout the semester, right? You could go through the write-up, but the first thing we want to be able to build this picture that you see right here. But we'll also use all the previous components that you've already built for MyTorch. So you've already built linear. We'll also need softmax, but we'll have to do some modifications to your previous implementations. So for your old linear could handle only 2-dimensional inputs and outputs. You'll have to modify it to handle inputs and outputs where this batch dimension can be an arbitrary number of dimensions, right? So you can have bxt xi, and you should be able to project it to bxtxo, right? Where I and O are your input and output dimensions respectively. You'll have to do the same for softmax. So essentially, you'll have to make it more generic. In your first in homework 1 P1, again, you took 2-dimensional softmax inputs to your softmax, applied the softmax operation on only the last dimension, and then you had your softmax output, right? Now here, you'll have to extend your softmax implementation to handle that same arbitrary number of dimensions. But also, you'll also have to be able to apply that softmax to any specific dimensions, right? That should be an argument, and an argument will be provided to you, and you'll have to. Sorry, yeah.
We don't need softmax only the feature, the logic.
Yeah.
And not the batch dimension.
We don't need it on the batch dimension, but the main problem is in your homework 1 P1, you had softmax applied. You had 2-dimensional inputs, right?
Yeah.
N times C, and then you could only apply to the last dimension.
Yeah.
But in this assignment, you'll have N times H times T times something, right? And then T times C, and you'll have to apply it to the last dimension again.
With T and C.
Just C.
Oh.
Yeah. So we're asking you to be more generic, but you'll still apply it on the last dimension. But you'll have to handle, the thing you'll have to handle is the arbitrary inputs, like arbitrary input size. So like you could, so you won't just get N times C, right? You could get N times T times C, N times, you could also get N times like NHTC. You'll see when you do the assignment. But you will apply softmax even for this assignment on the last dimension, but we're just asking you to make it more generic, all right? Because that's how PyTorch has it too. You could apply it to any dimension. So once you have your linear and softmax, you should be able to implement the scale dot product attention. Forward and backward equations are given in the write-up. And then you'll use all of these to form your multi-head attention implementations. And we have this thing. You should be able to test all. We've provided you a test suite, and you should be able to test and get immediate feedback for him. So you can implement things incrementally and test your feedback, test your implementation instantly, right? So this is the MyTorch part. So the reason we're doing this is for homework for P1 and P2. When you actually move to PyTorch, we won't ask you to use your transfer like multi-head attention implementation because it can be slow. We don't want to affect your training, right? There's all these optimizations that are done under the hood by PyTorch to make their implementation faster. So, but we still want you to know how multi-head attention works. So we're asking you to implement that for homework for your MyTorch library, right? All right, so you're done with MyTorch for now, and then we'll finally move on to the second task of homework for P1 is where you will train you'll build this decoder only transformer architecture, and then you'll train it to model text, right? So, all right. So before we, your first step would be to create your data set. But before we do that, we'll have this tokenizer. Essentially, what we're giving you is raw text, right? But model can't learn from raw text. So you'll have to you'll need a mechanism to convert this raw text to some kind of numerical representation. And you'll also need a way to convert that numerical representation back to the raw text when you're doing like generation or something, right? So for your homework for we'll provide this class called homework for tokenizer. That's what you'll be using to tokenize your text. But before we go forward, do we have any questions on Zoom? Hello? Oh, sorry, I was muted. Okay. No questions on Zoom?
No questions.
Okay, sounds good. So one thing you'll have to experiment for in this assignment is the tokenization. It's a hyperparameter for you, is what tokenization strategy do you want to take for your text, right? So we have this text, let's say, hi deep learners. Now you could tokenize it by character, where every character is a unique element, right? As you can see there. Or you can use this thing called subword modeling, where you can read more about a subword modeling. It's subword tokenization, but essentially, like we train this model essentially on this corpus of text, and then we specify, oh, like I want you to create a vocabulary that's constrained to the number I provide you, and then it learns this tokenization. It learns a heuristic-based tokenization scheme that is aimed at creating these tokens based on word frequency, based on like frequencies of subwords essentially. But you don't have to know too much about that. You can just know that you'll have these other tokenization strategies. But the larger the vocabulary, the shorter your sequence is likely going to be, right? So as you can see here, the tokenization that is done by character level produces a much longer sequence than the tokenization that is done by the 10K BPE. Sorry, we're using byte pair encoding as our tokenization scheme, which is a type of subword encode tokenization. But you can see the 10K tokenization has a much smaller length. Now this will affect first it'll affect your model performance, and it'll also affect how long your training can take, right? So if you have longer sequence to process per batch, it can affect your training time too. So that's something you'll have to manage, right? So once you'll implement your data set, which will essentially do what we were talking about previously, where you'll have to take your text, tokenize it, do the right shifting that we are talking about, and prepare the batch. So you'll have to implement your init methods, your length methods, your collate fn and get item. And once you're done with that, you can use this command to test your implementation. There you go. And it should test if you've implemented your data set according to the specification that is in the source files. Another thing to note is there's a lot of details and specifications that are in the source file. You have to ensure that you follow them as closely as possible, which is why we have these test cases to enforce that you're following these, because they all work in the broader context of this library, right? But you'll start incrementally, so you might not have that broad context yet. Right, so once you do your data set, you'll do your model implementations. So you'll implement the causal masking, which is where we create this mask so that the transformer is not able to cheat, as we discussed before, right? And then again, you'll use it to test your implementation. And then you'll construct the pad mask, which is the mask that is applied to the batch to ensure that your tokens are your padded tokens are not influencing the model in any way, right? You can visualize your mask, right? So we have the causal mask here. The white portions are true, essentially. So true means do not attend to these positions, and false means attend to me. You are allowed to attend to this position. And then we have bad masks, right? So here the white, as you can see, we have a bad size of variable length sequences, and the white portion is like, oh, do not focus on this part of the sequence, right? And then you'll merge internal. You won't have to do this. You will have to do this for PyTorch, but internally, PyTorch will merge both these masks to create what it calls like its final attention mask. It's everybody uses different terms, but yeah, I call it mask. Then you'll implement positional encoding, which is where the transformer gets its notion of order. And then you can also test your implementation, right? You can visualize your positional encoding. And then you'll move towards building your transformer. So in our library, we have this notion of a sub layer and the notion of a layer, and then the final transformer, right? So you'll first be building this self-attention, what we call the self-attention sublayer. Essentially, you'll just follow these pictures and implement the forward passes, right? Follow the doc strings, follow the comments that are there. And then we have tests for everything, so you'll be able to test your implementation. So you'll build the self-attention sublayer, you'll build the feed-forward sublayer, you'll combine them to build the entire decoder layer, and then finally, you will build the entire transformer decoder-only architecture, right? And the last library thing that you'll have to build before you can begin training is your decoding. So you're decoding. So we only require you to implement greedy search for this part. You can follow the instructions in the write-up. In greedy search, essentially, you're going to be selecting the It's very easy, right? You're gonna be selecting if you have this probability distribution of tokens and you want to determine what your next token should be, you're just gonna select the most probable token, append it to whatever you have generated so far, and then loop. And at every time step, you're just gonna select the most probable token. Right? So once you've done that, you'll have to implement your training loops a little bit. So you have your train epochs will set the loop for training for one epoch, validate will do the validation steps, whatever you've been doing so far, and generate will, you'll also have to set up how you're going to generate the text and the train methods. And that'll be your final implementation for this assignment. So once you're done with this, you can take your handout and your notebook to a GPU runtime and train your language model. And then you have your goal in order to get full points for this assignment is achieve a per character perplexity, which is our evaluation metric, below 3.5. Right. So that's what we have for homework 4P1. Now for homework 4P2, we are building an encoder-decoder model, encoder-decoder transformer model, which is, if you can think of it as like a conditional language model, right? So you want to, this is what we're modeling. You want the transformer to model the probability sequence of text tokens conditioned on these sequence of speech features, right? So towards that end, you'll be reusing some of the components that you built in homework for P1 towards homework for P2 to build this encoder-decoder transformer model from scratch and train it on the automatic speech recognition task. And then finally, you'll have to use it to transcribe the speech features on a test set and submit to Kaggle. And the metric that we will be optimizing for is CER, or character error rate. Right. So unlike the decoder-only model, where we were training on this corpus of unlabeled, large corpus of unpaired text, here we'll actually need paired speech and text data, right? So we want to model the probability of this sequence of text tokens conditioned under the given the speech features, right? And we want our transformer to model this conditional probability at each time step. So this is it's mostly the same. You'll also have to, the training process will differ in the sense that you have this encoder now, which will first take these speech features. We are providing you with sequences of 80-dimensional filter bank features as your speech representation. It will process it to create a sequence of hidden state representation, right? And then in your decoder, you'll have this extra sublayer called the cross-attention sublayer, which will attend to both its internal text token representation by the self-attention sublayer that we discussed previously, and it'll also cross-attend to the speech hidden representations that we're getting from the encoder, right? And then you'll get this sequence of hidden states, apply softmax, project to the vocabulary space, and then apply softmax to get this probability distribution for each token at each time step, right? So you could think of this as a conditional language model. It's just being conditioned on the speech features that we have. All right, we're using character error rate. And then again, you'll already have implemented greedy decoding in homework for part 1. You can use that for homework for part 2, and it's possible to cross high cutoff with just greedy decoding, but it might be harder. You'll have to might have to train for longer. So we also optionally ask you to consider implementing beam search. There's pseudocode in the write-up. And that might, like we've had situations where somebody had like 27 CER with just greedy search. And as soon as they implemented beam search and chose a decent beam width, they crossed the high cutoff. High cutoff was last semester was around 12 or something. So we definitely recommend implementing beam search. Can give a big boost, right? So you'll have to implement your ASR dataset, which will process paired text and speech, paired speech data and its corresponding transcripts, right? So this is similar to what you've been doing in your other homework so far. You will collect all your speech and transcripts in your init method, apply normalization, and then construct these nice block-sized batches by applying padding. And also you'll apply a spec augment to the speech features too. And then you'll implement your transformer, other transformer sublayers. Now, good thing is most of this you will have already implemented in homework for P1. So like both the sublayers you see in encoder and two of the sublayers you see in the decoder will be implemented in homework for P1. So you can reuse it in homework for P2. And you'll have to add this new sublayer that that processes the decoder sequences, but while cross-intending to the encoder output, right? Once you do that, we also have tests for all of these. All right, test your implementation. We put everything together to build the decoder layer. The encoder layer. And then finally build the entire transformer. We don't require you to implement beam search, but like I said, it's optional. But we have provided you with test cases for implementing beam search. So we would definitely recommend you to implement. And here's a test that will verify if your implementation is correct. Right? So again, once you've done all these implementations, you can take your handout and your notebook, upload to a GPU compute, and train your transformer, encoder decoder transformer for the automatic speech recognition task, right? So here's some tips and tricks that we want you to consider for homework for P2, right? So I'm gonna say it right out of the box that this model will be much more resource intensive than what you've been used to in the past, right? You have a bigger parameter limit, so you'll run a lot of risk. Your epochs, your per epoch time might be much longer, and there'll be a lot of risk running out of memory and stuff like that. But they can be managed through trade-offs. Right, and that's something you'll have to learn for this assignment, how to manage this trade-off between model performance and then your computational efficiency, right? This is also why we don't recommend you using Kaggle if you are using Kaggle, because it's going to be a real pain training these models in Kaggle. Right, so one way you could balance this trade-off is through your feature representation. We are giving you these 80-dimensional speech features, but you don't have to keep all 80 dimensions, right? You can drop some of the dimensions. If you learn about what filter banks are, they'll be like they'll have all these high frequency information which might not be useful for the speech task, right? So you can, this is a hyperparameter, you can experiment dropping some of the features and see to like speed up your training time. But then there'll always be this point where if you go too far, you'll lose too much critical information, and that will affect your model performance. Another thing to note is the impact of tokenization, right? So we are providing you with character level tokenization, subword level tokenization with vocabularies with 1K, 5K, and 10K vocabularies. Besides affecting model performance, they will also affect how long your training might take. Because like as we discussed earlier, using a character level tokenization might give you a much longer sequence than what you can get from, let's say, a 10K level tokenizer, right? So that will affect the number of parameters your model will have, and as a result, it'll affect the training time, right? And then it'll be your speech feature representation. So we take this speech features and we process them with this small model of stacked CNNs and LSTMs which we'll call speech embeddings. This has already been provided to you. Now here, as in your previous assignment, as in your homework 3 part 2, you can choose to downsample your speech sequence representation, right? Like the way you've been doing it in PBLSTM or in your CNNs if your stride is more than one. You can choose to downsample the representation that your model will see, and that can lead to faster processing times. It'll lead to fewer parameters, and consequently, you'll have much faster training. But then again, with all of these things, you'll have to manage. This is a hyperparameter that you'll have to manage carefully because too much downsampling will lead to loss of information. All right. Now, another thing we will ask you to do in the pursuit of like seeing how far you can push your model and improve your model's performance, you can also use your homework 4 P1 model in homework 4 P2. Now, homework for part 1 will take extremely short time to train. Like, right, you can train the entire thing in like, let's say an hour, right? An hour or 2 hours. But you can integrate your homework 4 P1 model in homework 4 P2, and this should be able to in 2 ways, and this should also help you kind of manage the trade-off, as you'll see. So one way you'll use it is in shallow fusion method. This is essentially using your homework 4 P1 language model that you've trained along with the ASR model just during inference, right? So while you're doing beam search, you're going to take log linear interpolation between the ASR model and the model that you trained in your homework 4 P1. And the intuition is that, oh, like your homework 4 P1 model was just trained on text, right? And it has been trained on a larger text corpus. So it should be able to model this, it should have a better linguistic context than your homework 4 P2 model. So you will help your homework 4 P1 model refine the predictions that your homework 4 P2 model makes, right? So you could use it that way just during inference. And in our internal evaluations, we have noticed it gives a little boost, but the amount of boost it gives will depend on the kind of model you've trained in your homework 4 P1. Now, the another thing you could do is if you see the decoder, you see the architecture of your homework 4 P1 model, right? This is the final architecture. Is there a way to? Let's compare these architectures side by side, right? Okay, this is pretty bad. Essentially, there's all these common layers, right? So if you train a homework 4 P2 model that has essentially the same decoder dimensionality as a homework 4 P1 model, you can import the weights of your homework for P1 model into your homework for P2 model, just the self-attention and the feed-forward network parts, and you can freeze them, right? And you can, this is what we have. 1 second. So you'll avail yourself to essentially 3 training strategies. First is cold start. You'll just train your model, start from the beginning, or you could use your homework for P1 model to initialize the common layers in your homework for P2 model and freeze them. Train your model with just the encoder unfrozen and the cross attention unfrozen. Once you've done that, you can unfreeze everything and fine tune for a few epochs. Now, if you do it this way, you won't have to train for as many epochs because you already have some learning that's been done in your homework for P1 that you can just transfer over to your homework for P2 model, right? And then another thing you can do is this training strategy we call progressive training, which is like a curriculum-based approach. So essentially, you might have to train deep encoder and decoder networks, right, for your final model. But training the entire thing will just be hard to like the per time epoch might be too long, right? So what you can do is this incremental training approach where you can start with 1 encoder, 1 decoder, train it, and then freeze the 1 layer of the encoder, 1 layer of the decoder, and then add another layer, right? And then you can just do this successive doubling every time, right? You start with 1, 1, then go to 2, 2, freeze the previous ones, go to 4, 4, freeze the previous ones, and this will help you manage your compute much more efficiently, right? It'll also take a shorter time than training the entire model from scratch because you're freezing everything you've trained previously. So once you've done that, once you've trained in this progressive manner, you can unfreeze everything and fine tune for like 10 or 15 epochs. And there you have it, you have your final model. So this will allow you to, if you're restricted on compute, this can allow you to like train these much larger models without running out of memory and without it taking too long per epoch, right? And this has also been shown to to lead to better convergence and have like a much more stable training experience. Like training the entire model might be a much harder task than progressively training each layer. You can also do other things. So essentially for progressive training, your base idea is you have to have this notion of difficulty, right? So your notion of difficulty can be how many layers, how complex is my model, or how much regularization I am applying, right? And then you have to have a way to schedule this difficulty progressively, right? So you start with an easy task and gradually scale up to these hard tasks, right? But there was a good analogy here that somebody. Yeah. So it's motivated by this core idea that the model that is trained that is trained on simpler version of the task can generalize more effectively to complex tasks. So you gradually increase the difficulty of the task. Now you can do this by like scheduling the layers you have at each stage, or you could also add, let's say, stage 1, I have no dropout. Stage 2, now I have dropout. Stage 3, I have no augmentation. Stage 4, I'll add augmentation, right? So you make your tasks harder at the same time increasing your model capacity and freeze everything previously. And that should allow you to, like training the whole transformer might take you like 15 minutes an epoch. Doing this kind of freezing, you can probably do it in like 4 or 5 minutes, right? Also, you don't have to, you could also choose to scale the amount of data that is available to you. You could split your data into these nice subsets and be like stage one, only train on this subset, add a layer, stage two, train on this subset. There's these various notions of difficulty in the write-up, and you can choose whichever one you'd like. There's something about gradient accumulation, like you'll probably not be able to fit, transformers sometimes require large batch sizes, but you'll probably not be able to fit that in your GPU. So there's this neat trick to give you the same effective batch size without using the without setting the same batch size, right? So you can have a batch size of, let's say, 4096 by just using a batch size of let's say 8, right? And that you can learn about gradient accumulation and use it as a hyperparameter. Now, another thing we want you to do for this assignment is we'll be logging viciously. We have provided you with this framework that will log everything imaginable. So every time you run an experiment, we will log your checkpoints, but also the attention visualizations and the generated text during each training loop, right? So here's we would recommend you to monitor these things too, because they can inform you about how your model is performing. The two key things we will be plotting is your decoder self-attention and the decoder cross-attention. So self-attention will say how, will show you how your decoder is attending to its attending to the input to the text token sequence while making its predictions. And you'll see a strong diagonal dominance here. If you don't see it, that means there's something wrong with your decoder, right? And the more interesting thing, in my opinion, is we'll also plot the decoder cross attention, where we'll see how the decoder focuses on the speech representations while making a prediction, right? Now, it won't be a perfect diagonal, but because the speech sequence might be much longer than your text sequence, right? But we know that we know that for ASR, our inputs and outputs are at least order synchronous. So if I say hello, like whatever speech features correspond with H will all be aligned sequentially, right? So you should see this like diagonal like structure. And if you don't, that means there's something wrong with your decoder. Right? And we would also ask you to monitor your generated text. At the beginning, you'll see it's complete gibberish. It's kind of cool, actually. It'll start off by being completely gibberish, and then the transformer will be like, all right, it learns to align the lengths, right? So you'll see your input and output lengths, input and target lengths start to align, but it's still gibberish. But then it learns, then you can start seeing the texts forming some structure, and then finally towards the end you'll see like a much better input and target correspondence. You can also use this to kind of debug, right? All of these things you can use to debug. For text, let's say like you see it's performing really well on short sequences, but not so well on like long sequences. So maybe you'll have to maybe you're doing too much time downsampling, or maybe you'll have to increase the maximum length your transformer can accommodate, things like that. More on that on the write-up. Right? So there's a lot to do in this assignment. This is your last assignment. You'll have a lot of implementation, but our professor asked us to include this blurb, which we fully believe on, is that it's a culmination of everything you've been doing in all your previous assignments. And yeah, we believe that you can call yourself a deep learning specialist if you've gone through and implemented everything in this assignment. Any questions? Any questions on Zoom? Oh, sorry, there are questions. Oh, sorry. When will pizza come?
Hello, hi.
Sorry, yeah.
Hello, hi. I'm asking about, I saw you said that you you don't r- recommend cargo. So I'm just wondering what exactly do you recommend?
So we would recommend using Colab. Uh, Kaggle you can still do, but just know that it might take you longer. But the environment I would recommend the most is PSC. It's fairly easy to set up. I'll make a video on how to set it up for this assignment, right? And that will have, there's a problem here, right? You have all these students on PSC who are using V100s, and if you're not on PSC, you're using T4s, and you're essentially limiting yourself, right? It sucks, it's just the nature of DL. Yeah, sir.
Is there any value in using multiple?
And also, okay,
One second. Sorry, could you say?
Distributed data parallel?
You can use distributed parallel. We don't support it as a course, so all implementation will be up to you. But yeah, you can use it. There's value, of course. But yeah.
But there's no value in instead using model parallelism, like splitting up the model.
The models won't be that large for like this to happen. Yeah. Yeah, model parallel won't be that helpful. DDP would be helpful. Yeah, I don't think the models will be. We have a 30 million parameter limit. Model parallelism won't be helpful. Yeah, sorry, you had a question on Zoom?
yeah. I was asking, do you also need, do I also need the GPU for the PP1?
Yeah, homework for P1 you need a GPU, but for P1 you can do it on Kaggle. It's a very lightweight model. Like you'll see it'll train very fast.
Oh, okay. Thank you.
Cool. Like if you use PSC, one epoch will take 30 seconds. Right. Approximately how many hours are required to pass the early cutoff for homework for P2? We've provided this config for homework for P2, and the config hyperparameters are set up in such a manner that you can cross it in 10 epochs, less than 10 epochs, right? As long as you've implemented everything correctly. We've tested this 5 times in different environments, and sometimes it crosses in 7, sometimes it crosses in 8, but it always crosses like at below 10 epochs. Right. Any other questions? Another thing to note is you'll need an efficient way to so you're implementing this library, right? And then you'll have to import your library components to your notebook. So you'll need an efficient way to get your handouts in and out from whatever compute you're using. I recommend GitHub, uploading your thing to GitHub, and you can just clone every time you make a change. But yeah, we have some strategies some practices that you could follow. And there's setup instructions for all the following platforms. So PSC, Colab. Another thing is we recommend you implement everything locally first. We're providing you with the subset data set to the point where you can do almost all the implementation work locally before moving to a compute. So we recommend setting up your environment and doing everything locally first. And then, yeah, these instructions differ based on what compute environment you're using. But this is all we're supporting. Anything beyond that, it'll be hard to find help for this homework. All right, any other questions? Pizza will come now. Oh, yes. So this is just the notebook I created for the bootcamp. You have to follow the notebook that is in the AutoLab. It's essentially the same notebook. I just added like a bunch of pictures and stuff. Yeah. Oh, no. So it's possible for you, our high cutoff is one of the good thing about this assignment is that if you implement a correct transformer, it'll be rather easy crossing our high cutoff. The challenge will be like the time it takes to train the model, and then doing all the implementation work. There's a lot more implementation than your previous assignments, right? So If you implement even a reasonable model, you should be able to cross high cutoff. But then how much further you can take it and all that, that depends on you. And you can manage like the time it takes to train your model using the training strategies we mentioned, like using your 4P1 model to initialize your homework 4P2 model, or training progressively, right? Any other questions before I end and order pizza? All right. There's somewhere. All right, thank you guys. Thank you guys for listening. Best of luck for homework for both the parts. April 25th. Also, yeah, you have a longer time for your early cutoff too this time because of the amount of implementation you have to do.